3176 is a heavy-duty four-stroke cycle diesel engine designed specifically for the on-highway truck market. The 3176 represents the leading edge of technology in heavy-duty engines. Design innovations, such as a two-piece articulated piston, aluminum spacer deck, and the complete integration of engine electronics, set the 3176 apart from the conventional diesel engines of both the past and the present. These features combine to give the 3176 unmatched fuel economy, reliability, and durability. By the early 1980s, it had become evident that new engine technologies would have to be brought to bear if Caterpillar, or any other diesel engine manufacturer, was to prosper in the rapidly evolving market environment. A combination of increased government regulation, prompted by legitimate environmental concerns, stronger competition, and more demanding market expectations dictated totally new approaches to diesel engine design. In order to meet these challenges, in 1984, Caterpillar embarked on a development program to create a totally new diesel engine. That concept would become the 3176 diesel engine, the next generation heavy-duty fleet engine. Before Caterpillar set out to design the 3176, several critical design objectives were identified. This engine would be all electronic and equipped with ATTAC for fuel economy and emissions control. We set out to design an engine that at first production would have to be just as reliable as the mature 3406B and improve from there. The drivability of the 3176 would compare favorably to the 3406B, ensuring that the driver would not have to pay the usual smaller displacement penalty of extra shifts and poor performance on grades. In some cases, meeting these objectives has required a radical departure from conventional diesel engine design, but the Caterpillar 3176 diesel engine was never intended to be conventional. In the past, products were developed by using a design, build, test loop. Production began only after the end of repeated loops. The 3176 project, on the other hand, used concurrent process development. Design analysis and production process development were performed concurrently during the design process. Finite element analyses was used extensively to predict the behavior of parts long before the first iron was cut. These and other innovations allowed substantial savings of time from concept to production. Never before has a Caterpillar product been subjected to the kind of high-tech scrutiny that the 3176 has been. Beginning with finite element analysis during the design phase, the 3176 has been thoroughly tested and evaluated at every step. After a thorough design phase, the 3176 has had thousands of hours of lab test and extensive road testing. During the 1980s, the 10-liter heavy-duty truck engine concept has been enjoying growing worldwide acceptance. At the same time, increased competition within the trucking industry has forced trucking companies to do all that they can to contain costs. Containing costs in the trucking business really means fuel economy. Add these factors to an increasing willingness on the part of the government to face up to serious environmental issues, and a climate exists with both great market potential and serious constraints at the same time. In order to take advantage of this setting, Caterpillar needed to set the stage for the 1990s and beyond with an all-new engine. Caterpillar needed a rugged engine that would deliver great fuel economy while meeting ever-tightening emissions requirements at the same time. It would have to be an engine that represented both engineering leadership and obvious value to the owner. The 3176 is an inline six-cylinder with a 125 by 140 millimeter bore and stroke. It has a total displacement of 10.3 liters and a dry weight of 882 kilograms. The 3176 is a metric engine with metric fasteners. English fasteners are used for OEM attachments such as starter, air compressor, and flywheel housing. English pipe plugs are also used. The 3176 relies on electronically controlled unit injection to achieve top performance. Engine electronics control fuel injection rate and injection timing, governing, air-fuel ratio control, and horsepower ratings. Initially, power will span 250 to 325 horsepower. With 882 kilogram dry weight, the 3176 is one of the world's lightest weight-to-horsepower ratio heavy-duty truck engines available. The weight-to-horsepower ratio at 300 horsepower is 6.48 pounds per horsepower. The 11-liter Detroit Diesel Corporation Series 60 stands at 8.90 pounds per horsepower, and the 14-liter 300 horsepower 3406B has a ratio of 9.17 pounds per horsepower. Illustrated are the performance curves for the 300 horsepower rating at 1800 RPM and the 325 horsepower rating at 2100 RPM. Note the high torque rise with a peak torque of 1150 pounds per foot at 1100 RPM. The 300 horsepower rating has a strong 31% torque rise over a wide operating range. The 325 horsepower at 2100 RPM has 1225 pounds per foot at 1200 RPM for a torque rise of 53%. This translates into fewer gear shifts, enhanced gradability, and less driver fatigue. Note the relatively flat horsepower curve. More of the engine's horsepower is available over a wider operating range, again improving performance and eliminating extra shifts. Fuel consumption is an excellent 0.312 pounds per horsepower hour at 1800 RPM rated, and this is at the 6.0 NOx EPA emission level not required until 1990. At first production, the 3176 will be certified for all of North America. It will be emission certified to the January 1st, 1990 EPA NOx and particulate laws and meets the current California CARB and the December 1988 Canadian requirements. Other ratings available for the 3176 are illustrated here. The engine will be available in 4 horsepower families: 250, 275, 300, and 325 horsepower. All 2100 RPM vocational ratings exceed 50% torque rise, and all 1800 RPM economy ratings exceed 30% torque rise. Excellent performance characteristics result. Factory set ratings are indicated with asterisks. These will be the only ratings available from the factory. All others can be reset at the OEM or in the field with either of the electronic service tools. Engine design features are OEM end-user driven. The high torque rise gives the user big engine drivability in a smaller package. The hardened liners, crankshaft, camshaft, and other big engine features give the 3176 big engine durability for the long haul. Even the main bearings are comparable in size to ones found in a large truck engine, ensuring that the 3176 has an extra margin of dependability designed in. In general, features are equivalent in design to a larger displacement engine, providing big engine performance, durability, and reliability at a lower cost. The 3176 exhibits a number of design approaches quite different from what has been standard in the past. The engine is available in an air-to-air aftercooled, ATTAC configuration only. The engine is completely computer controlled. The conventional mechanical fuel pump governor arrangement will not be available. The engine block is a 2-piece design, a cast iron base with an aluminum spacer deck. All are radical departures, made possible by advances in technology and made necessary by changes in the market environment. The 3176 utilizes an electronically controlled, mechanically actuated unit injector fuel system. This helps account for the lack of fuel lines and the clean appearance of the engine. The engine electronic control system, an integral part of the engine design, offers quicker and more accurate control of timing and air-fuel ratio. The electronic control module, the system's computer control, is visible on the left side of the engine. Other features to note from this side of the engine are an available fuel filter with a hand priming pump. Both Bendix and Midland air compressors are available. The cast aluminum oil pan is reversible. The power steering pump drive is located just beneath the air compressor, and aluminum SAE No. 1 flywheel housing is standard. The right side of the 3176 has just as many innovations as the left side. The cylinder head is a uniside head with both the exhaust and the intake on the same side. This increases turbo efficiency. The exhaust manifold is a pulse-type manifold with 3 cylinders entering each side of the divided turbo housing. This helps to shorten the path the exhaust gases must take and reduces heat rejection. The shorter the path to the turbo, the more energy the exhaust will pack. Other features to note are a gear-driven water pump conveniently located at the right front. An external gear-driven oil pump is just below the water pump for easy access. A Poly-V belt fan drive is used. A sealed plate-type oil cooler. 2 engine-mounted oil filters, one full-flow spin-on, the other a spin-on bypass filter. 2 spin-on bypass filters will be available, a standard paper element type as shown, and an optional centrifugal type with disposable rotor. The 3176 block assembly is a unique design consisting of an aluminum spacer deck and a gray iron deep-skirted block. The spacer deck forms the upper portion of the block assembly and furnishes the cylinder liner water jackets and support for the camshaft. The cast gray iron block provides the seat and locating bores for the liners and support for the crankshaft. The block skirt extends well below the center line of the crankshaft. This deep skirt is serpentine-shaped to increase stiffness and reduce weight by providing only the space necessary for the crankshaft counterweights. All threaded holes for fastening the cylinder head, flywheel housing, front timing gear housing, and the front engine support are in the cast iron block portion of the block assembly. There are no water jackets in the cast iron portion of the block. All are in the spacer deck. 2 oil manifolds are provided for engine lubrication. The lower right side manifold, in the cast iron block, supplies oil for the piston cooling jets and the crankshaft bearings. The upper left side manifold in the spacer deck supplies oil for the camshaft bearings and valve mechanism. Both manifolds are cast solid and rifle drilled to assure unobstructed passages for the oil. The cast aluminum spacer deck forms the upper portion of the block assembly and provides the water jackets and support for the camshaft. The spacer deck also allows the liner to be cooled almost to the top, allowing the top piston ring to be placed much higher on the piston. The aluminum spacer deck reduces engine weight, helping to achieve the excellent weight-to-power ratio without sacrificing strength. The microstructure and alloy content of the aluminum spacer deck is closely controlled to guard against galvanic damage. The spacer deck utilizes a low copper alloy aluminum to inhibit the conduction of stray electrical currents, which can cause galvanic corrosion. Aluminum is prone to galvanic corrosion only when the engine is improperly grounded or coolant recommendations are not followed. Any potential for corrosion in the 3176 is controlled by grounding the cylinder head to the frame to the starter, and the frame to the battery. The cylinder liner is a mid-support design seated on the top face of the iron block and piloted below the seat and at the bottom of the block. The liner is cast iron and the bore is induction hardened for additional life. A precision honing process yields superior cross-hatching for excellent oil control. Liner sealing is above the seating surface with a rectangular seal placed into a groove machined into the aluminum spacer deck. The mid-support design allows for greater cooling around the very top of the liner, where the greatest amount of heat is generated. This allows the engine to use a high top ring piston design for low crevice volume. Coolant, supplied through an integrally cast manifold in the spacer deck, enters the spacer deck at each cylinder and flows around the liner and into the cylinder head. Since there is no top flange, the liner can be cooled almost to the cylinder head joint. This is important because of the high-mounted compression ring that gives the piston its low crevice volume, which is critical for emissions control and fuel efficiency. The crankshaft is a single-piece steel forging with induction-hardened journals, fillets, and sealing surfaces. Flange-mounted dual-lip Teflon seals with hydrodynamic grooves running on induction-hardened crankshaft wear surfaces are used for oil control. Hydrodynamic seals use a combination of multiple spiraling seal lips and shaft rotation to continuously pump the oil back into the crankcase. The seals are assembled to the front timing gear cover and rear seal housing with bolts and a rubber O-ring for easy service. The main bearings are steel-backed aluminum with a copper-bonded lead tin overlay. The center and end main journals are at the end of their respective oil passages. Oil enters the crankshaft from oil passages drilled through the lower block into the numbers 2, 3, 5, and 6 main bearings and travels through the crankshaft oil passages to the rod journals and the numbers 1, 4, and 7 main journals, front, center, and rear respectively. This keeps these 3 bearings from being drilled or grooved. The greater area provides the maximum oil film thickness possible at these critical locations. The main bearings are 100 millimeters in diameter and 35 millimeters wide. The rod bearings are 82 millimeters in diameter and 43 millimeters wide. This gives both the main and rod bearings a projected area of 110 square centimeters, which is comparable to large displacement engines. The piston is a 2-piece articulated design consisting of a forged steel crown and a forged aluminum skirt. Both are assembled to the connecting rod by the piston pin. The 2-part design allows the piston crown to be made from high-strength steel. This allows the piston to withstand much greater pressures and temperatures than conventional aluminum is capable of. A nye-resist band is no longer needed because all 3 rings ride in ring grooves in the steel crown. The aluminum skirt is isolated from the usual combustion and gas loads, which allows for simpler design. The aluminum construction also decreases the reciprocating mass of the piston. Because the piston can articulate, the skirt is separate from the crown and its heat distortion. This reduces both noise from piston slap and heat caused by friction. Illustrated here is the use of finite element analysis to predict the structural behavior of a component before it is even built. This allows the engineer to play what if without cutting any iron, or in this case, forged steel. An oil cooling chamber is formed by the lip forged at the top of the aluminum piston skirt and the cavity behind the ring grooves in the crown. Cooling jet oil enters the cooling chamber through a drilled passage in the skirt and returns to the sump through the clearance gap between the crown and skirt. Note the flow of cooling oil behind the rings. Cooling in this critical area lowers the ring's operating temperature, reducing potential carbonization and ring sticking. The pistons have 3 rings located in grooves in the steel crown. The top ring is a barrel-faced keystone type with a plasma face coating. This coating material is very hard for added wear resistance. The top ring is placed high in the piston to decrease crevice volume, lowering emissions and improving fuel economy. The second ring is taper-faced with a chrome-plated face coating. The bottom oil control ring has a spring expander and is double-railed, profile ground, and chromed face coated. 4 holes drilled from the bottom oil control ring groove to the interior of the piston drain excess oil from the ring. The connecting rod is a steel forging, shot-peened and heat-treated for long life. It has a 12-degree taper at the piston pin end, allowing it to fit into the piston cavity while making the maximum use of available space to withstand the downward force of combustion and inertia loads. In other words, the bore is narrower at the top when the connecting rod is viewed from the side. The bottom of the piston pin bore is wider because it has to withstand the shock of the cylinder firing during the power stroke. a steel-backed bronze bearing is pressed into the pin end. The large end rod bearing is steel-backed aluminum with a copper-bonded lead tin overlay. The cap is aligned to the shank with two 6.4 millimeter dowels and retained by two metric M14 by 1.5 cap screws. The cap screws are tightened using the torque turn method of tightening, which ensures less variation in their final torque. A balance pad, found on the large end, is provided to control the weight of the finished rod assembly. The cylinder head is a one-piece gray iron casting with 4 valves per cylinder to optimize breathability. The Uniflow port design features intake and exhaust manifolds on the same side of the head, enhancing breathability versus a cross-flow design. To cool the head, a shelf is cast between the top and bottom decks. It directs coolant across the bottom deck and around the valve insert bosses and unit injector seats. Coolant flows up around the unit injector sleeves, over the exhaust port, and exits into the engine water manifold. Each cylinder is a separate compartment, eliminating wide variations in temperatures and hot spots. The 3176 intake and exhaust valves and valve seat inserts are not common. Their design has been optimized for their job. Intake valves have a head diameter of 45 millimeters and a seat angle of 30 degrees. The exhaust valves are 42 millimeters in diameter with a seat angle of 45 degrees. Again, the valve diameter is comparable to that found in larger engines. The valves are faced with an iron base, chrome nickel alloy, and have hardened steel stems for exceptional wear and heat resistance. The valve seats are replaceable. Replaceable valve guides are precision machined with a threaded bore for improved lubrication. The cylinder head gasket is a wrapless wire ring solid core gasket with a non-asbestos facing material. The head is clamped to the liner and block by 6 bolts per cylinder, with 2 of the bolts shared between cylinders. The camshaft is forged steel with carburized and hardened bearing journals and cam lobes for long wear. 3 lobes are needed for each cylinder in order to operate the unit injector, exhaust, and intake valves. The cam rotates in 7 bearing bores, precision machined into the aluminum spacer deck. Oil for the positive lubrication of the camshaft bearing journals is provided by the spacer deck oil manifold. As the spacer deck is made from cast aluminum, press-in aluminum bearings are not needed. Remanufactured spacer decks, which are rebored, will use a press-in bearing to bring the bore back to original size. The camshaft is located high in the engine to keep push rods as short as possible, assuring a stiff valve train. The injector and valve mechanism is a push rod and rocker arm system with roller lifters. The roller lifters are swing arm type actuated by the camshaft. Roller lifters reduce friction and wear compared to slipper followers. The rocker arms are arranged in units, with each unit consisting of a support bracket, shaft, exhaust rocker arm, intake rocker arm, and a unit injector rocker arm. Each unit is doweled and bolted to the top face of the cylinder head and can be removed as a unit for easy serviceability. 2 rocker arms of different lengths operate the intake and exhaust valves. A rocker arm pushes on a bridge which in turn moves the 2 inlet or 2 exhaust valves. The valve rocker arms and bridges are cast ductile iron for toughness. The bridge has an integrally hardened contact pad, and the rocker arm has a pressure lubricated pivot bearing. The injector rocker arm is a steel forging with a replaceable hardened steel insert for the pushrod cap. A special skirt surrounds the injector pushrod bridge connection to retain the pushrod and protect the engine from damage in the event of an injector seizure. 2 8mm pushrods are used for the valves, and 1 15.8mm pushrod is used for each unit injector. All of the pushrods are made from solid steel bar with a spherical end at the lifter and an upset cup at the rocker arm end. The mechanically actuated unit injector combines high-pressure pumping, an electronic actuator, and injector spray nozzle into a single compact unit. The electronic unit injector is an integral part of the 3176 state-of-the-art fuel system. Computerized electronic control of the exact time and duration of the injection provides the most precise metering and timing of fuel available. Refer to the Fuel System section for a more complete explanation of unit injector operation. The gear train is located at the front of the engine and drives the camshaft, water pump, air compressor, and the power steering pump. There are 6 gears for the basic engine, plus 2 for the air compressor and power steering pump. The gears are high contact ratio spur gears, carburized and hardened. The isolated cam drive gear is nitrided. Machined notches in the camshaft gear provide the reference points for the electronic engine speed and position sensor. The oil pump is an externally mounted fixed clearance gear type pump located on the front timing gear housing just below the water pump. The external mounting greatly improves serviceability. It is driven by the front gear train with a flow rate of up to 149 liters per minute at 2100 RPM. A high pressure relief valve is located in the filter base to protect the filters from excessive pressure during cold starts. The oil pump bypass valve is controlled by the engine oil manifold pressure rather than the oil pump outlet pressure. The manifold oil pressure then becomes independent of pressure drops caused by the oil filter or oil cooler and maintains a more constant oil pressure throughout the engine over a wider operating range. Refer to the lubrication section for a more complete explanation. The water pump is located on the right front of the engine, just above the external oil pump. By mounting the water pump there, instead of behind the fan drive, serviceability is improved. The pump has a capacity of 250 liters per minute. The pump shaft rides in ball bearings in the pump housing and the front timing gear cover. The impeller is cast gray iron and is press fit onto the water pump shaft. The pump housing and volute are aluminum die castings. A cartridge-type water pump seal is located on the inlet side of the pump to provide good cooling flow around the seal. It can easily be replaced by removing the externally mounted volute housing and pulling the impeller from the shaft. The 3176 takes advantage of the extra reliability and simplicity offered by wide poly-V belts for the fan and alternator drive. In the drive to reduce emissions and improve engine efficiency, the engine cooling system takes on increased importance. Careful attention has been paid to the design and testing of the advanced cooling system used in the 3176. The 3176 cooling system consists of a gear-driven water pump, oil cooler, water inlet and outlet manifolds, temperature regulator, and temperature regulator housing. Coolant flow for the oil cooler, cylinder head, cylinder liner, and air compressor is furnished by the gear-driven water pump on the right side of the engine. The integrally cast water manifold in the spacer deck distributes coolant to each cylinder. Approximately 65% of the coolant flow is around the cylinder liner. The remaining 35% flows directly to the cylinder head. The cooling system regulator, or thermostat, is a no-leak, full-flow bypass type. The regulator directs all, part, or none of the coolant through the radiator depending on engine temperature. The system is based on a water inlet temperature of 91 degrees Celsius, a water outlet temperature of 99 degrees Celsius, and a flow rate of 250 liters per minute. Total heat rejection is 21 BTU per horsepower minute, with about 16 BTU from the engine jacket water and about 5 BTU from the air-to-air charge air cooler. Heat rejection has become an extremely important design parameter to accommodate the aerodynamic trucks found on the road today and to ensure that the engine is as efficient as possible. The proper coolant mix has always been important. Too much or too little ethylene glycol in the coolant mix can result in damage or overheating. With the addition of aluminum in the engine, maintaining the proper coolant mix becomes even more important. The coolant recommendations for the 3176 are no different than recommendations for our other heavy-duty truck engines. 30 to 60% ethylene glycol with 3 to 6% inhibitor concentration. and water with a 6 to 8% inhibitor concentration. Note that the amount of conditioner required depends on the ethylene glycol concentration. More conditioner is required for a 50-50 mix than a 30-70 ethylene glycol water mix. In general, if you add 4 ounces of conditioner for each gallon of ethylene glycol and 5 ounces of conditioner for every gallon of water, you will be within recommended limits. Individual circumstances may require more conditioner. A coolant conditioner cartridge is available. The lubricating system is designed to provide 110 degrees Celsius filtered oil at 40 psi under all operating conditions. A major feature is that the oil pump bypass valve is controlled by oil manifold pressure rather than oil pump pressure. The oil manifold pressure is independent of oil filter or oil cooler plugging, ensuring a constant flow and pressure. The lubricating schematic includes these features: a thermostatically controlled oil cooler bypass valve to maintain the optimum 110 degrees Celsius oil temperature for longer component life, a high-pressure relief valve located in the filter base to protect filters and other components during cold starts. A damaged filter could allow contaminants into the lubrication system, damaging internal engine components. The relief valve opens at 101 psi. A symmetrical oil pan allows for either front or rear sump. A choice of 2 optional engine-mounted spin-on bypass oil filters, either the standard paper cartridge or an optional centrifugal filter with a disposable rotor element. A sealed plate-type oil cooler is located above the oil filter base. Oil flows from the pump, through the cooler, and into the primary oil filter. Bypass oil goes directly to the bypass filter. The 3176 has a centrifugal bypass oil filter available as an option. The filter works by directing the bypass oil through a hollow centrifuge cartridge and out 2 opposed nozzles in the bottom. The oil pressure causes the cartridge to spin in excess of 6,000 RPM. Centrifugal force overcomes the force of the oil flow and removes the relatively heavier contaminants by holding them against the side of the spinning cartridge. After the disposable cartridge has trapped about 0.7 kilogram of contaminants in this way, it needs to be replaced. The air intake and exhaust system is designed to provide the air for combustion in the adequate amount at the right pressure and temperature. The exhaust side of the system must dispose of the exhaust gases, but not before wringing out as much energy as possible before it is lost out of the stack. To handle this rather big job, the 3176 uses a combination of air-to-air aftercooling, a pulse exhaust manifold, and the latest in turbocharger technology. The intake and exhaust system is optimized for air-to-air aftercooling. A TAC is the best system for lowering diesel engine charge air temperatures. Cooler charge air is better because cooler inlet air is denser, allowing more air to be packed into the cylinders for more complete combustion. Cooler air also reduces exhaust emissions, which allows improved injection timing for even more improvement in fuel efficiency. To optimize engine performance and acceleration, a pulse exhaust manifold system with a divided turbocharger turbine housing is utilized. The front 3 cylinders are connected to one entry on the split turbine housing, and the rear 3 cylinders connected to the other. This keeps each exhaust gas pulse, due to firing order, from interfering with the one before it. This conserves exhaust energy for the turbocharger. After charge air flows through the air-to-air aftercooler, it goes to the intake manifold, where it is distributed to 3 Siamese plenum chambers, 1 for each 2 cylinders, in the cylinder head, and flows through the inlet valves into each cylinder. The 24-valve head provides excellent breathability. The intake and exhaust port arrangement on the 3176 is a distinct design, quite different from conventional diesel engines. The intake port design is referred to as a Siamese plenum. You will notice in the illustration that each pair of intake ports are a mirror image of each other, connected by the plenum, hence the name. The exhaust ports are series flow, one behind the other, with 30-degree skewed valve placement. This port arrangement provides exceptional airflow and, because the exhaust flow distance in the water jacket is reduced when compared to a conventional design, lower jacket water heat rejection is obtained while delivering more heat energy to the turbocharger. The 3176 fuel system is not just new, it is totally new. This electronically controlled fuel system is a radical departure from conventional fuel system design. The conventional diesel engine fuel system is a product of years of evolution. Except for size, many of today's fuel systems have the same general appearance and work in much the same way that their predecessors did 50 years ago. The 3176 fuel system, on the other hand, is not the result of some incremental step in fuel system development, but the next step in technological progression. In order to achieve the kind of precise fuel control required to meet emissions requirements, while at the same time improving economy and performance, computer control of the engine is necessary. The fuel system routes fuel from the transfer pump through the ECM and unit injectors. In both cases, the fuel is used for cooling before it returns to the fuel tank through the fuel return manifold. A pressure relief valve is located between the fuel return manifold and the tank to maintain sufficient pressure. A pressure sensor is strategically placed to warn of a plugged secondary fuel filter. A hand priming pump is located on the secondary fuel filter base to fill the system after filter changes or manifold draining. The fuel transfer pump is a gear type and is located at the left rear corner of the engine. The fuel transfer pump is mounted to the spacer deck and is driven by the camshaft through two 45 cross-axis helical gears at 0.96 times engine speed. At 2100 RPM, pump flow is 7.5 liters per minute versus an engine demand for 0.88 liters per minute at 325 horsepower. This provides more than sufficient fuel for cooling the ECM and the injectors. In order to generate the higher injection pressures required to achieve the ambitious economy and emission goals set for the 3176, the high-pressure fuel pump and injector have been combined into one component. When the plunger pressurizes the fuel, instead of flowing through external fuel lines and then into the injector, the fuel unseats the injector check valve directly. With no external lines, higher pressures can be achieved. The job of metering fuel, previously handled by the scroll or sleeve back at the fuel pump, is now built into the solenoid-activated spill port. All of the moving parts previously found in the governor, rack, and timing advance have been replaced by the spill port and the ECM. Not only does the unit injector offer the greater inherent reliability of fewer moving parts, it delivers maximum control over fuel injection duration and timing. Many of the benefits are due to the ability to providing a transient timing map and the flexibility to tailor the control to specific applications. The electronically controlled, mechanically actuated unit injector fuel system combines high-pressure mechanical injection with precise electronic control. This single, compact unit assures greater fuel economy and superior emissions control. The injector is mounted in the cylinder head at the cylinder center line. Fuel is supplied through an external manifold that bolts to and connects with drilled passages in the cylinder head. In order to better understand the operation of the unit injector, let's look at the actual injection sequence. With no pressure applied to the plunger from the camshaft, a spring keeps the plunger retracted. Fuel flows through the open feed port into the barrel and continues through the injector passages fed by the low-pressure fuel transfer pump. During this period, the pressure is too low to unseat the spring-loaded check valve at the injector's tip. Most fuel passes through the injector to the open fuel spill valve and out the spill port to a fuel return manifold and back to the tank. This flow of fuel cools the injector. As the camshaft rotates, it starts to drive the plunger down. After the plunger closes the feed port, the barrel is full and the injection of the fuel is controlled by the ECM. If the ECM doesn't send the signal to start injection, the fuel in the injector is displaced through the spill port as the plunger continues its downward travel. When the ECM signals to start injection, the solenoid pulls the fuel spill valve up, closing the fuel's path to the spill port. With this valve closed, pressure elevates quickly at the injector tip as the plunger continues to be driven down by the camshaft. At 5,500 psi, the force of the spring-loaded check valve is overcome and the valve unseats, allowing fuel to be injected into the cylinder. Fuel will continue to be injected until the ECM signals the solenoid to open the fuel spill valve. With the fuel spill valve open, fuel passes out of the spill port and the pressure at the injector tip drops, allowing the spring-loaded check valve to reseat. When this valve reseats, injection of the fuel stops. The plunger continues down, displacing fuel out the spill port. Many of the emissions and performance benefits of this state-of-the-art electronic unit injector control system are due to the capability of providing the engine with more accurate and flexible injection timing and fuel delivery control. The 3176 was designed as a total electronic engine from the ground up. The electronic control system is integrally designed into the engine's fuel and air inlet exhaust systems. This advanced electronic approach provides increased control of timing and air-fuel ratio with fewer moving parts. Just as any computer system uses a combination of hardware and software to accomplish its job, the 3176 uses sensors, a transducer module, a speed buffer, a personality module, and the electronic control module to accomplish its job. These are not just add-ons, they take the place of components that are found on a conventional engine, namely the governor and timing advance. But the hardware, advanced as it is just the tool. The software is the brain that tells the tool what to do. We will look at the tool first. The electronic control module is the brain of this advanced fuel system, with the electronic microprocessor housed inside. The ECM is designed to survive the environmental hazards a modern truck engine must endure. It has been developed to withstand extremes of heat, cold, salt, road dust, oils, and humidity. The internal electronics are also protected from both electromagnetic and radio frequency interference. It is resilient mounted to resist vibration to the engine and cooled by a continuous flow of fuel. Mounted to the ECM is the personality module, which contains the operating program and the performance maps for that particular engine. It also works with the ECM to store customer-specified parameters specific to that engine family, identify a selected factory engine rating, and log faults for diagnostic troubleshooting. We'll cover fault logging to a greater depth later. It is the personality module that can be reprogrammed with the new engine parameters. The transducer module is mounted directly to the ECM and houses the boost pressure sensor. It also measures ambient air pressure through the air cleaner. The remaining sensors are remote mounted and connected to the ECM by the engine wiring harness. Besides the pressure transducer module, other sensors are necessary to give the ECM the information it needs to control the engine. Mounted at the front of the engine is the camshaft pulse sensor and the coolant temperature sensor. The optional high coolant and inlet air temperature switch sensors are also mounted at the front of the engine. The optional coolant level switch would be mounted by the OEM on the radiator. An integral part of the system, the vehicle speed buffer, provides output to drive the speedometer as well as a logic level signal for input into the ECM. In other words, it tells the ECM vehicle speed. The ECM has an ATA data link which allows it to communicate with other microprocessor-based devices that are compatible within the ATA SAE standard. In the future, these can include trip recorders, electronic dashboards, and maintenance systems. The data link can also reduce the duplication of truck-mounted sensors by allowing controls to share such information available from the 3176 system as engine RPM, vehicle speed, boost pressure, throttle position, diagnostics, engine ID, and customer-specified parameters. The 3176 advantage comes when the hardware is combined with the software. It is the software that contains the logic that translates the pre-programmed information, including customer parameters, into performance. The main engine features are electronic governing, air-fuel ratio control, programmable ratings, injection timing control, system diagnostics including fault logging, and the engine retarder interface. The 3176 governor is built into the ECM and is an electronic all-speed governor which functions much like the typical Caterpillar mechanical governor. It has added features like programmable low idle RPM, which allows the customer to set the low idle anywhere within the 600 to 750 RPM idle range. If the truck's mirrors rattle at 625 RPM, for instance, the customer can reset low idle to 630 RPM. The 3176 electronic governing also eliminates governor overrun. This removes one more variable from the equation and makes the truck easier to spec and its performance easier to predict. The advanced electronic system has full authority over engine fuel delivery. Advanced electronic engine controls more accurately control smoke than conventional systems. Depending on the rating family, several optional ratings and torque levels can be programmed using the Electronic Control Analyzer and Programmer, ECAP, or the 3176 Digital Diagnostic Tool, DDT. The engine can be re-rated within certain parameters as conditions dictate, giving the customer flexibility. Total electronic control of injection timing to optimize performance for starting, fuel consumption, and good drivability is standard on the 3176. Engine timing is computer controlled by the ECM, controlling the exact timing and duration of the unit injector spill valve operation. The subsequent computer-controlled timing ensures much quicker throttle response. Diagnostics are a vital part of any advanced electronic system. The quality of the 3176 electronic diagnostics are unmatched. Diagnostics are built in, ensuring components operate properly. If a failure should occur, the operator will be alerted via the dash-mounted check engine light. Inexpensive Caterpillar service tools are available to read out the numerical fault code to make service easier. No need to swap out boxes in the dark. It takes the guesswork out of troubleshooting. The 3176 electronic control module is equipped with an integrated system diagnostics package. One of the key features of this package is intermittent fault logging. One of the most common problems for maintenance personnel is the intermittent fault that occurs out in the road and then cannot be recreated. This is handled in the diagnostic package by storing not only the fault, but the circumstances when it occurred. These would include speed, RPM, oil temperature, boost, and so forth. All of this information can then be retrieved using an electronic service tool like the ECAP or the 3176 DDT. How does this electronic engine handle a retarder? The 3176 can interface an engine retarder through the control unit. It is this kind of complete integration of the retarder function with the computer that ensures optimum performance. A jake brake is available from the factory as optional equipment. The ATA data link, discussed earlier, allows the 3176 electronics to communicate with other microprocessor-based devices that are compatible within the ATA SAE standard, such as trip recorders. Offered as an attachment, this module provides comprehensive monitoring of crucial engine components. Various degrees of warnings are provided to the driver, depending on the severity of the fault detected. All required software, engine wiring harness, and additional sensors are provided. This module continuously monitors oil pressure, coolant temperature, coolant level, engine overspeed, and air inlet temperature. This information is available across the data link for electronic dashes and trip recorders eliminating the need for many OEM-installed sensors. This also ensures that the ECM can keep its electronic eye on more variables for more complete fault reporting. All abnormal conditions are fault logged, as well as notifying the vehicle operator. The Advanced 3176 offers more than just the enhanced engine control mentioned earlier. The same hardware and software that provides the edge in engine performance also has the flexibility to shape vehicle performance. The 3176 can reach beyond the engine compartment to provide the kind of environment that enhances overall vehicle performance. Some vehicle capabilities, such as cruise control and the PTO governor, add extra convenience. Others, such as road speed limiting and progressive shifting, help to control fuel consumption, which translates into reduced operating costs. With the 3176, there is no need to add an extra cost add-on cruise control because one is built in. More than just a convenience item, cruise control greatly reduces driver fatigue and improves fuel economy through less variation in vehicle speed. The cruise control sets vehicle speed via OEM-supplied on-off and set-resume switches. Vehicle speed is maintained at the programmed speed until the brake or clutch switches are actuated or the system is turned off. For applications requiring a PTO governor, the 3176 has an isochronous power takeoff governor, controlled by the cruise control switches. The 3176 offers more precise control of PTO operation, coupled with greater operator convenience without added expense. While a truck may have a gear-fast, run-slow spec, there is no easy way to ensure it's not driven as a gear-fast, run-fast truck. A user-specified, pre-programmed vehicle speed limit can be programmed in at the OEM and modified later by the owner, allowing the owner to spec gear fast, run slow with confidence. By assuring that the truck will in fact be run slow, the 3176 will show even greater improvements in fuel efficiency. One of the factors that separate the fuel-efficient drivers from less fuel-efficient drivers is the use of progressive shifting. Progressive shifting is using only the RPMs necessary to get into the next gear. Needless winding up the RPMs in each gear as the driver is getting up to speed wastes both fuel and time. The programmable progressive shifting feature in the 3176 allows it to limit the acceleration rates at specified vehicle speeds and gears. This is an engine parameter that can be tailored to both the operating environment and to the transmission, rear axle, and tires. It all adds up to better fuel economy. When the 3176 is installed in a vehicle equipped with an electronic dash, the diagnostic code display is included as part of the dash. If, on the other hand, the 3176 is installed in a vehicle that is not equipped with an electronic dashboard, diagnostic codes can be read as sequenced flashes on the check engine lamp using the cruise control switches. Recognizing that while excessive idling can burn unnecessary fuel, there are times when the operator would like to allow the truck to idle for a few minutes after he pulls off of the highway. To balance both concerns, a programmable idle shutdown has been built into the 3176. The operator can pull into a truck stop and go in for lunch, leaving the truck idling for 5 minutes to cool off. If the operator needs the truck to remain idling for any reason, the timer can be overridden. Also, the timer only works when no vehicle speed is detected and the parking brake is applied. Either of the Caterpillar service tools can program or reprogram this feature. The 3176 engine control has been designed to easily interface to various manufacturers' auxiliary engine brake systems. A Jake brake, capable of 250 brake horsepower at 2100 RPM, is available as an option. The Jake brake control uses the enable signal from the ECM and dash-mounted switches to apply retarding to 2, 4, or all 6 cylinders. When equipped with a smart dashboard, fuel consumption information is available in real time. Average fuel consumption information is also available. Continuous feedback has been shown to improve driving habits and cut fuel costs. Despite all of its sophistication, The electronics that are a part of the 3176 require special service tooling. The cost of electronic service tooling can conceivably offset any gains realized by using an electronic engine. The 3176, on the other hand, uses either the existing Caterpillar ECAP service tool with an add-on 3176 adapter chip or the dedicated 3176 DDT. A dedicated handheld DDT service tool is available for the 3176. This inexpensive service tool, only a few $100s versus thousands for similar competitive service tooling, can read faults, check parameters, and reprogram the 3176 personality module. A minor limitation is that the password programmed into the engine must be numeric. The standard Caterpillar ECAP electronic service tool can perform all of the necessary service and programming functions for the 3176, including alphanumeric passwords. A low-cost conversion chip and a 3176 breakout cable are required. A low-cost conversion module is available for existing ECAP tools. A breakout cable is also required. A somewhat higher-cost module for 3176 electronic timing diagnostics will also be available for the ECAP tool. Because the 3176 was designed as a truck engine from its inception, careful attention was paid to eliminate additional cost items like suppression equipment. Several 3176 features illustrate the importance Caterpillar placed on noise attenuation. Noise reduction is built in. The unique combination of the underframe, isolated camshaft drive, and the isolated mounting of the valve covers and oil pan mean the 3176 is quieter to begin with. The 3176 easily passes the drive-by noise requirements without the necessity of extensive truck-mounted sound suppression. A lightweight cast aluminum underframe fitted to the bottom side of the cylinder block prevents the block sidewalls from resonating. Not visible from the outside of the engine, the underframe is easily removed for bearing service. The camshaft drive uses a unique isolated gear to reduce torsional vibration. A patented hydraulic system of 12 shock-absorbing dampeners connect the drive gear to the cam. This system dampens inherent torsional vibrations to reduce gear backlash for lower mechanical noise emissions. In addition to the other noise suppression, the valve cover base and oil pan are isolation mounted, dampening vibration more. If necessary, an easily attached front cover panel is available as an attachment. The 3176 is a heavy-duty, 4-stroke cycle diesel engine that was designed specifically for the North American on-highway truck market. As a leading-edge competitor in the heavy-duty engine market, the 3176 is designed to compete with the world's best. Design innovations such as a 2-piece articulated piston, aluminum spacer deck, and the complete integration of engine electronics set the 3176 apart from the conventional diesel engines of the past. These features combine to give the 3176 unmatched fuel economy, reliability, and durability. Of particular note is the wider rated RPM range and the increased torque over the L10, the lighter weight versus the Series 60, and the excellent fuel economy versus everybody. Not included in the slide, but something to note, certain ratings of the L10 are being marketed in Europe with air-to-air aftercooling. As of publication, these ratings were not available in North America. A full range of attachments for most any truck application is available for the 3176. This list, while far from complete, does provide a flavor of what is available. Separate engine arrangements are available for the Allison HT and MT automatic transmissions. No flywheel will be used in these arrangements. 3176-based cruise control and progressive shifting will not be available and are not compatible with automatic transmissions. The 3176 truck engine is not evolutionary, it is revolutionary, setting new standards for fuel economy, performance, reliability, and durability. The 3176 incorporates a new level of performance for the 1990s